Okay, we're going to now work the problems that you guys did in group form. I will try to label clearly which problem I'm working at any time, and if you had success on it already, you can simply skip to that next one that you might need. So this is going to be problem number 1. And it reads that the mass in grams, okay, of 1.255 moles. Gosh darn it, here we go. Okay, now the way to think about all of these mole problems is everything goes through the mole. What I mean by that is if you have a mole here, you can get 2 grams and you can go from grams to moles. If you have moles, you can calculate liters, and if you have liters, you can calculate moles. And if you have a certain number of particles that is given to you, you can go to moles, and from moles you can get a certain number of particles. Now what you need to recognize is there are one-step problems. Grams to moles, moles to grams. Moles to liters, liters to moles, and of course moles to numbers or numbers to moles. Those are all one-step problems. But some problems are two-step. One example of that, if you're given a certain number of grams and you ask for the liter value, you convert grams to moles and then you convert moles to liters. And that of course is a two-step problem. In this problem right here, it's asking for the gram value, so what is the mass in grams, and you're told the number of moles. So that's going to be a one-step problem. However, whenever you see a weight value, whenever you see grams, you must first calculate the molar mass of that material. And so calcium nitride is Ca3N2. And what we're asking is, what is the weight if I have 1 mole worth of these molecules? And the format here is really, really important. So you'd write down calcium equals, you'd write the molar mass down, which is 40.08, and you'll notice there are 3 of them. So there's 3 at that weight, therefore you've got 120.20. So that's the weight contribution of calcium. Nitrogen is going to be 14.01, and you'll notice there are 2 of them, and therefore you've got 28.02. Now if we sum these up, you get 148.26. That is the weight of a single molecule. But if you have a mole worth, or 6.02 times 10 to the 23rd worth of this many molecules, then you get this weight in grams per mole. So we call this the molar mass. Now to set this thing up, what we're going to do is dimensional analysis. So again, quick reminder, whenever you see grams in the problem, bam, you have to calculate the molar mass. And you want to use this method as a format. Now, what we're going to do is dimensional analysis. And when you do dimensional analysis, the first thing you do is you take whatever number they give you and you write it down. 1.255 mole, put it over 1, Then you write another train track. Create the fraction. If you have moles up here, you have to have moles down here, and you close it off. That is a standard move. Take the number given, punch it in over 1, train track, whatever you have up here, you put down there. Okay, now right here, this is going to be a unit ratio. And so what it says is, if I have 1 mole of this material, it weighs 148.26 grams. So this is the molar mass. Notice our moles cancel here. And if in fact you multiply it through, it's going to equal to 186.07 grams. Now the question is, does this make sense? Well, 1 mole weighs this many grams, but I don't have 1 mole. I have 1.25. So the number should be bigger than this, and it is. So one might assume that your answer seems reasonable, and it is. So let's take a look at the next problem that was given to you. So we're going to take a look at problem number 2. Now, as you saw in the first problem, the way to think about this is everything has to go through the moles. So if you have moles, you can get to grams, vice versa. If you got moles, you can get liters, vice versa. And from moles, you can get numbers. Now, you'll notice in this case that you have a gram value given here. Therefore, once again, the first thing you have to do is get the molar mass of tin-4 dichromate, which is the weight of 1 mole worth of this molecule. To do that, here's how you set it up. So over here, SN CR 04 2. That is the tin-4 dichromate molecule. What we got to do is get the weight of this. So again, big issue is formatting. Your strategy is to write down the first element, which is SN10. There, its weight is 118.71. There's just one of them, so you get 118.71. You've got Cr, chromium. Cr weighs 52. And you have 2 of them. Notice this sub value is going to be 2 of these whole units, and therefore there's 2 of the chromiums, and you're going to get 104. And then you have oxygen. Oxygen weighs 16. Since one of these dichromates has 4 of them, if you have 2 dichromates, there's 8 of them. So it's 16 times 8, which is going to equal to 128, following the 2 decimal rule. So if we now add that up, you get 350.71. That is the atomic mass of one of these molecules. But if you count out 6.02 times 10 to the 23rd of this many molecules, that is the weight it will be in grams. And that is the weight of 1 mole worth. So this is known as the molar mass. So now what we do is what we do every day, Pinky. We put in the first number given to us. And so it's going to be 666.66, interesting number, grams, always put units, over 1, put parentheses, put another parentheses, put grams down here, and this now becomes the unit ratio that we need. And so once again, 350.71 grams per mole. So notice what we're going to do is we're going to put 350.71 grams is 1 mole. Now this problem was given to you with intent, meaning in the last problem you had moles on the bottom, grams on the top. In this case you have grams on the bottom, moles on the top. How do you know which is which? Well, the units you have up here have to be the units that you have down there. And the result is you get 1.90 moles of SnCrO4 2. Box our answer. Now once again, does this make any sense? Well, 1 mole of 10,4-dichromate weighs 350, but I have 666, so I should have more than 1 mole. And in fact, I do. So the number is reasonable. Right, so let's take a look now at problem number 3. So this is number 3. If you got 1 and 2 correct, you can jump straight to here. Now once again, you make a big deal out of this. All mole problems are like a road map. They're going to either go from or to grams to moles, they're going to go from or to liters, or they're going to go from or to the number of items. And in this case, it's asking for liters taken up by a mole. So we're going to go from liters to moles, and that's a one-step problem. Now, many students are going to jump and start to do this idea that, well, I have O2, I have oxygen, oxygen weighs 16, there are 2 of them, blah, blah, blah. That is not what you want to do. Why not? Because there's no grams asked for in this problem, so I don't need a molar mass at any time. What is being asked is liters to moles. Therefore, I simply have to set my basic ratio up. So I'm going to take my number given, which is 2.5 moles. So I take 2.5 moles divided by 1. Next, I put moles down here, close it off, and that's where I'm going to work on my unit ratio. But then what's my unit ratio when it comes to gases? My unit ratio is 22.4 liters of any gas will equal 1 mole of material. So if I have 1 mole of O2 or 1 mole of argon, it's going to take up this much volume, no matter what kind of gas it's at. So I'm going to use my unit ratio, which is 1 mole equals 22.4 liters. My mole cancellation takes place. I multiply it out, and I get 56 liters of O2. Once again, is this reasonable? Well, 22.4 liters is 1 mole, but I have 2.5 moles. So I'm clearly going to have significantly more than 2.4 liters worth, and sure enough I do. Therefore, this answer seems very reasonable. Hello? So let's take a look now at the last problem, which is going to be problem number 4. It's constantly being given to you. Grams can go to moles, moles can go to liters, and moles can give you the number of items. Now, in this problem, it gives you the number of items, and it's asking for moles. So you're going to go from a number of items to moles. That's a one-step problem. So I don't see weight in here at all, no grams. So I'm not going to undergo a conversion of weights to molar masses. So I'm going to place the number given, 4.22 times 10 to the 5th is the number of items. I must use a symbol number, it's not a hashtag, over 1. Hashtag down here, actually number. So this is going to be my unit ratio. What's my unit ratios? Well, I'm going to go from the number of items to moles. So this must be the number of items to mole ratio. And 6.02 times 10 to the 23rd is 1 mole. So what we're going to do is we can cancel out the number of items to number of items. We're going to now multiply it through. Now, I'm going to do this since it allows us to see the scientific notation again. So we're going to multiply our numerators, and that's going to give me 4.22 times 10 to the 5th, and that's going to be divided by 6.02 times 10 to the 23rd. Now, when we do that, we take 4.22 divided by 6.02, and that's going to give you 0.22. And then you take 5 minus 23. Oh, mistake. It's going to be 0.70. My bad. And what we do here is we take 5 minus 23, and that gives you 10 to the minus 18th. Putting it in true scientific notation, you get 7.0 times 10 to the negative 19 moles. Is that number reasonable? Let's find out. 1 mole is 6.02 times 10 to the 23rd. I have only 4.22 times 10 to the 5th. 10 to the 5th, that's a really small number compared to the 10 to the 23rd. So I suspect I have a very small amount of mole. And in fact, that's true. So that seems to be a reasonable answer.